Right. Lecture, I don't know which lecture we are on. Lecture square, I don't know. It was supposed to be lecture 18, but lecture 18 in terms of number of times that I've recorded myself, but I don't know in terms of with respect to the syllabus, but we are actually on time. We are doing finite element solution in 2D today, and then we're going to do verification and validation on Wednesday. So I've caught up to the syllabus, which is great. And yeah, we'll do just a little bit more finite element solution in 2D today. Before that, just a couple of announcements. Homework due today. For a couple of you that were asking me if you still have to do stuff for problem 1, yes. I only gave accidentally half of the solution. So the first one, which is plotting the temperature contour, but I did not do the gradient. So that one you still have to do for problem 1. So plotting the gradient. Then problem 2, I think is, oh, I guess that was problem 2. Problem 1 is the strong form to weak form, which again, if you have questions, come to office hours. Should be very similar to the one that I did in class, just a couple of small details. Then yes, problem 2, I did half of it, but you still have to do the gradients. Then problem 3, I think that one is probably the more involved, but we have talked about it in class and in the lab on Friday, the Python lab on Friday. So hopefully that's doable as well. And then the last one is just the project. And for that one, you just need to plot, find the solution of your problem and then plot it. I've posted maybe 3 of those on the Slack. So if you haven't found the page in the SAT book, or it's not one of the 3 that I've posted, then ask on Slack, and then I'll put it on Slack, so that if other people have the same problem, they can look at that. I think that's it for announcements for today. Then, yeah, as Zach was pointing out, there is an exam next week. And actually, I was finalizing the bank of questions yesterday. So I have that. And it's going to be the same format as the first exam. It's going to be on Brightspace. It's going to be open all day on Wednesday of next week. And then you can do it at every moment that you want. We won't have officially class, but I'll be here, and then I'll basically just be answering questions for the exam in case you want to do it after that session. That's it. It covers only material from it doesn't have anything from the first part. It's all related to the 2D stuff that we have been doing. So it's not cumulative, it's just the 2D heat transfer problem. Any questions? Yes. An hour and a half. Just repeat the same strategy. I finished the bank of questions and I've sent it to the TAs, and then they will advise whether we need to remove a problem or whether the time is appropriate. As I think about it, it's 1.5 hours, and then I think it should be, similar to the first exam in my view. But I'll get the feedback from KU and Tina. Any other question? Cool. All right, then let's get to it. It's just more of the same. So I'm just gonna repeat myself, but repetition, I think it serves a purpose. If you remember what the weak form of the heat transfer problem is, this is the same that I had in the last set of slides, is the integral of the gradient of W times D is the conductivity matrix. But again, for the purpose of this class, we're only gonna do a scalar. For for isotropic conductivity. Equals minus the integral over the boundary Q of the shape functions times the fluxes plus the integral over omega of the weight function times the source term. And this has to be true for all the W's that vanish at the boundary. So this basically, this U0 is W equals 0 at gamma T, where temperature is known. Same as last time. This is what we need to solve with the FE. How do we solve with FE? The next thing that we introduce is discretization with finite elements. And we have talked about basically triangles and quadrilaterals. Only linear, there's quadratic as well, just as in 2D, in 1D there was, linear, quadratic, but we are not gonna do any of the quadratic stuff for the 2D, just linear. For triangles, you can set up the shape functions in terms of XY. And actually the solution that I did on Friday is in terms of XY. And what I have on the exam is mostly with the triangle with the shape functions in terms of XY. So I would say mostly this for the exam. I do have one small question with the Sayeta. So for the linear triangles, you can define your shape functions directly in terms of XY. The interpolation is, the function is just the sum of the shape functions times the nodal values. This is one of the problems. This is problem 2 of the current homework. The gradient, which is what I didn't do. I did this one, but what I didn't do was this one. But what is the gradient? The gradient is the sum of the gradients of the shape functions times the nodal values. So that one is the one that you needed to do. These shape functions in terms of XY they look bad. They are kind of ugly, but at least this interpolation and this gradient interpolation is straightforward. All you need to be able to do is get the derivative of the shape functions and then just evaluate at the corresponding XY that you want. Now, this is not very convenient for integration, as you probably saw for problem 3. If you actually want to do the integral, then you can get an ugly integral with the 2 lines, for instance. So if you want to do integrals, it's better to map things to the parent domain, to these psi eta coordinates or psi 1, psi 2 coordinates. That has its own problems. And so even though the shape functions look really, really easy, the problem is that now you need to interpolate both the geometry and the temperature. So you can interpolate the x coordinates as the sum of the shape functions times the nodal shape coordinates. And then you need to get the Jacobian, which is this 2x2 matrix that is in the lecture notes. For interpolating the function, you can also just sum the shape functions times the nodal values. And the main difference is in how do you calculate gradients? Because at the end, you want gradients with respect to xy, but you can only directly get gradients with respect to psi 1, psi 2, because the shape functions are functions of psi 1, psi 2. So if you want to get gradients with respect to xy, you get gradients with respect to psi 1, psi 2, and then multiply by the inverse of the Jacobian. That's for triangles. Then for quadrilaterals is the same as the triangles. So you have functions in terms of theta, which I've given in one of the previous lectures. You need to evaluate again x and the Jacobian. And then the interpolation is the same, sum of the shape functions times nodal values, and then gradients are the same, inverse of the Jacobian times gradients with respect to psi eta. Any questions about that? Sort of the overview. They will do a little bit more examples. And then Okay, last thing that's it. This is sort of the entire of the second part of the course that we have been doing. So weak form, a lot of finite element interpolation, and then when you put this finite element interpolation into the weak form, you get a system of equations. You get a definition for the stiffness matrix, and you get a definition for the force vector. What do they look like? This is what I have here. So the stiffness matrix ends up looking something like that, where you have gradient of the shape functions, and you basically just have all combinations, right? So you have gradient of the first shape function times D or K. If you have the matrix, you have a matrix D times the gradient of shape function 1, and then you just have all combinations. So 1 dotted with 2. And here depends how many nodes you have, what's the size of your matrix. So if you have a triangle, then this is 3 by 3. If you have a quadrilateral, this is 4 by 4. And what does the force vector look like? Is the integral of the shape function times the source term. And again, how long is this vector? Depends on how many nodes you have. The book uses this notation. So I just wrote it here so that you know what the notation of the book is. I use more this notation. So the book uses these matrix notations, but these are exactly the same. It's just a different notation. Again, these are the explicit for the triangle. Then these are the explicit shape functions. This is the notation by the book. For the gradients of this B basically has the gradients of the shape functions. This is D, and this is the gradient of shape function 1. This is the gradient of shape function 2. This is the gradient of shape function 3. The book again uses this notation for the stiffness matrix. I just want to have it here. You don't have to do it with this notation. It's just if you go to the book and you want to not get lost with what the book has with respect to what I have been writing, is everything is the same. It's just notation is different. So this BDB is the same as what I have here. Is this basically these dot products of the gradients, just in a different notation. The force vector, if it's constant, then no integral needed. It's just area over 3 times the source term times 1, 1, 1. This is what you needed for your homework. Then once you have the stiffness matrix and the force vector, you assemble into the global system of equations. We have done that before. I'll have you do one example now. And then finally, you can depend, if you number your essential nodes first, then you can do the matrix partitioning. And then the solution is this. I did that on Friday. So any questions so far about the entire process? Otherwise, we'll just do a few examples. So I won't talk about the fluxes just yet. I'll create the force vector of the fluxes, but I'll let you work on this and try to set up basically do that. And then the only thing that I will do is the Q, the flux vector. That one I'll do. So I'll give you maybe 7 minutes to get the system of equations KDF or KTF for that one, minus the flux terms, and then I'll just do the flux terms. It's problem 8.4 in the book. You can talk to each other. You can do it in pairs. Did I put some text there? So what are you going to do first? Let's solve the problem. Yes. What is your idea?
Idea.
Yes. Okay, good. Great. So, yeah. But in order to get this KDF, what do you need for every element? Right. So what is the stiffness matrix for the triangle? For what I did last time. It's right there. It must be a little bit after that. It's right there. So that is the stiffness matrix. And in particular, this is for your homework for wow, you should do it. These gradients should be constant. You have the differential functions and actually the notes from A. Those gradients, maybe you scroll down a little, that might have done it all the time. Yes, that one. So this one. These are the gradients of the shape. these are the ones that you need. Gotcha. So again, what you need to do is go back up. You need yes. What you need to do is create one that then you need to get variance of the shape. So we go and get the variance of the shape down below. And then once you do that, then you need to these are concepts. So actually say there's nothing to make the detail. Get the variance of the shape. Thank you. So we get the yes, yes. You can do the other ones as well. If you want like that. No. Okay, then go with the X, Y. You actually don't need the shape functions to the gradients. I mean, technically you need the shape functions because the force, but the force is a constant. The source term is a constant. The gradients, yes. So yeah, that you don't need to value the entire shape function. All you need is the gradient. So just take the derivative because the shape function actually has a lot of terms, and then just one term that multiplies x and one term that multiplies y. So the gradient really you only need those two terms. That should be somewhere. It's actually in my current slides. That image is have something like x. Very so these yeah, one would create the first. It is actually just that and yeah, you know, well, that one normally if you look at trying to play one of the principles is right this matrix percentage that's better than like that's fine. Yes. Yeah, but this is so unique. That is yeah, so it's just one over there. I mean, because you have 1 over 2 times the area, so I guess you have 1 over 2 times the area, then times 1 over 2 times the area, but then when you integrate, that is times the area. So it ends up being, I guess, 1 over 4 the area. One of the area will cancel out. Either cancel it out or just do it with 1 over 2 area, and then calculate the b to the b. But you can see at the bottom. So k is just a times b times b times b. You can see that at a. All right, let's do this so that we can do one more example. All right, so I want to do this one. What you need to do in order to assemble the global system of equations is for every element, there's only one element here. But for every element, you will need to calculate the stiffness matrix and the force vector, right? And so here, just one element, we'll do our mesh. So our mesh is gonna be one. It doesn't matter which way you do it, it should give you the same. I'm just gonna do 1, 2, 3 for my mesh. And so what is the stiffness matrix? The stiffness matrix is the integral of k greater than n1 dotted greater than n1, integral of k greater than 1 dotted greater than 2, integral k greater than 1 dotted greater than 3. It's going to be symmetric, so you don't need to do all of them. This, and then what I have in the notes above, another way of calculating this is with the B matrix. So this is what I have been writing. And then what the book writes is it writes, I'm gonna skip the D, but this is BE transpose B. This is book's notation. It's the same thing, it's just in a much more compact format, where that B is what you saw in the previous slides. That B should have basically every column should be one of the gradients. But they are the same. So my notation and the book notation, they are the same. Yes.
Why are those 3 blank?
Oh, this is just symmetric. I just I'm lazy. I don't want to write them again, but it's the same. So if the whatever entry is here is gonna be here, but they are not blank. There's some number there. So either way you calculate it, it's gonna be correct. I saw a bunch of you doing it with the B, so let's just do it with the B. This one is 1 over 2 times the area of the element, and then I'll just go up here. So it's gonna be y2 minus y3, and then x3 minus x2. Let's do that. So y2 minus y3 is gonna be 0 minus 0.5, so that's minus 0.5, and then 0 because it's x3 minus x2. Then I'll just try to do it relatively quickly. Let's see what's the other one is y3 minus 1 y1 and x1 minus x3. So y3 minus 1 y1. So y3 minus y1 is 0.5. And I think the other one was x1 minus x3, which was minus 0.5. Hopefully I did it correctly. And then the last one is y1 minus y2 and x2 minus x1. y1 minus y2, 0, and then x2 minus x1, 0.5. 0, 0.5. All right, so that is the B. the area of the element, I guess, is 0.5 by 0.5 over 2. So I guess that's times 2, that's 0.25. So this one is, I guess, -2, 0, 2, -2, 0, 2. Hopefully I'm not making mistakes along the way. All right, so this is the B matrix. Again, this is nothing but the gradient of the shape function 1. This is the gradient of shape function 2, and this is the gradient of shape function 3. And again, the K matrix is just the integral of BE transpose BE. Note that this BE is constant, right? So because BE is constant, this is this, which is nothing but the area. So the integral of nothing is just, or 1 is just the area, times BE transpose B. Okay, so what is that? So the area, which was 0.125 times B transpose, so -2, 0, 2 minus 2, 0, 2, times -2, 2, 0, 0, -2, 2. You can do all of this with MATLAB or Python. I don't know what this is. So this is a 3 by 3 matrix, and whatever this is. So I guess, yes.
Should you include the constant K?
Yes, correct. You are correct. Very good. Which was, I don't know what the K was. So does someone have the 3 by 3 entries of the K? It's like K times. And I don't mind if you do this with MATLAB. Yes.
Okay, we'll have the K in front. 0.25, -0.25, and 0. And then -0.25, 0.5, and -0.25. 0, -0.25, and 0.25. That's the K multiplied. I think the K was 2.
That's with the K multiplied, or?
Yeah, just take out the K.
Okay. There we go. So otherwise, this, I don't care if you do it with Python or MATLAB, but let's say that this is the stiffness matrix for the element. In this case, there's no need to do assembly since there's only one element. So there's no need to do from, the single stiffness to the big stiffness matrix. That's one thing that we need. The other thing that we need is the force vector. Again, the force vector, if you were to actually do it, this is similar to your homework. You will need to integrate the first shape function times the source term, the second shape function times the source term, and the third shape function times the source term. But because the source term is constant, this is just S times the integral over the first shape function, the integral of the second shape function over the triangle, and the integral of the third shape function over the triangle. And that one, you don't actually need to do the integral. This is just area over 3. So this is just S times area over 3 times 111. And this also in the slides above. So if you substitute the S and the area and 3, I don't know how much this is, but it's like 1 over 3 or something like that. 0.417. Yes, Andrew? Eight times this. It does look like the 2 and 2 here will give me 4 times over 4 will give me 1. 8. I'm not sure if it's 8. Because the K, what is the value of the K? Two. But then, so 4, 1, 2. Correct, yes. I think it's times 8. Cool, almost there. The one thing that I promised that I would do was the flux term. So this gives you the force vector, this gives you the stiffness matrix, and then your system of equations is that stiffness matrix times the temperature equals the force minus the flux term. And that one I need to tell you what that flux term is. So this is 2 then, minus 2, 0, minus 2, 4, minus 2, 0, minus 2, 2, times T1, T2, T3 equals, I should add the reactions, 0.417, 0.417, 0.417. This is K times the temperature, the force vector, reactions, and force Q. For the force from the flux, this one I won't ask in the exam because I really don't. It's a little bit more complicated, so I'm just going to tell you what it is, and I'm not going to ask for it in the exam. But basically, we have a flux here, and we have a flux here of 10. Now, a flux, if you see the units, the flux is in watts over meter, right? And our equation at the end is in watts. So the equation that we have at the end is KD equals F is in watts because it's an energy balance. So, and if you recall what the flux term is, the flux term is the integral over the boundary of W times the Q. So what this leads to is a vector of 3, which will have the integral of the first shape function, the integral of the second shape function, and the integral of the third shape function. So it's going to be a vector of 3 by 1. But the key thing is that these integrals are over the boundary. So we need to integrate the shape function times the flux over the boundary. And long story short is just the flux times the length of the edge over 2. You can think of it in this way. We have a flux of 10 watts over meter, we're gonna multiply that by the length of the edge. That's gonna give us the total amount of watts that are fluxing in, and we're just gonna split it evenly into this node and this node. So 10 watts per meter, we're gonna multiply by the length of the edge. So that's gonna be 5 watts total that are fluxing through that boundary, and then we're just gonna split it. 2.5 of those watts are gonna be put into the top node, and then 2.5 watts we're gonna put in the bottom node. And then for the other one, we have again 10 watts per meter times the length of that edge, which I don't know how much that is, but it's I guess Pythagoras theorem for that length. And then we're gonna split it in two, and we're gonna put basically half of each of those total watts into each node. But the proper definition is basically we are integrating the flux over the edge with the shape function. That's where we get the half from. Does that kind of make intuitive sense? All right, so then for this one, this is 10 times 0.5, that's 5, and then we're gonna split into 2, so 2.5 and 2.5 for nodes 2 and 3. So for that one, I'm gonna do 2.5 and 2.5 for nodes 2 and 3. And then for the other one, I don't know what the length of the edge is. So if you can help me to get the length, so 10 times the length of that edge, that will give us the total watts that should be going in, and then we're just gonna split it in 2. So if someone can tell me. The actual, okay, 3.35, all right. So let's do, and that one is between nodes 1 and 3. All right, and so the reactions, for which ones we know the temperature, but we don't know the flux. So the first two have essential boundary condition. So these two, we know the temperature, so we don't know the reaction. And then the last one, we don't know the temperature. So that's the system of equation. The only unknown is temperature 3. Yes.
The flux on the boundary, do you add or subtract?
Let's see. So depends on which way it is, whether it's going or outgoing flux. We will subtract. So we just follow this. So we would have to subtract that. And so it depends on which way here. There's no specification, so I'm just gonna follow the notation from the book. But if you have fluxes that are going into your domain, then you would add. If you have fluxes that are going out of your domain, then you subtract, because it's an energy balance. So you're either pumping energy in or taking energy out. And here, because it's not specified, I'm just gonna follow the notation from the book, is that positive fluxes are outward fluxes. So if they give you some value of Q, the book assumes, for example, that if you just give a positive value of Q, it's gonna be an outward flux. That's why it has a negative sign. But that's, it could change. So I would say if there's no specification, follow the notation of the book. Otherwise, if it explicitly says it's outside, then you add it in the right-hand side. If it's positive, then it's going into you're adding energy. So you would put it as a positive on the right-hand side. But here it's an outward flux. So that's why we subtracted. Cool. All right. That's it. I'll see you on Wednesday.